11.1. We're starting the chapter over statistics, descriptive statistics, so you can see is what we're focusing on in this particular lesson. Chapter 11 deals with all types of inferential statistics. So let's get going first with our bell ringer here. On number 1, it says find the rectangular coordinates for the point 3, pi over 4, given those polar coordinates. So 3, pi over 4 is polar, means we're going to be on this third circle, somewhere on this third circle, and specifically that somewhere is the pole pi over 4. So if I go to pi over 4, where these two meet, this would be my point A right there. And it says find out what those values are in rectangular form. Well, the formula we learned last class is to find your x, you will take the r and you'll multiply it by the cosine of theta, where for any polar coordinates, the points come in r, theta. So the x value would equal 3 times the cosine of pi over 4. And I'll pull up a unit circle in a second. The y value is going to equal r sine theta, and y then, when I plug in, I substitute my values, will be y sine of pi over 4. Okay, so now what I'm going to do first is I'll show you by algebra what the values are. Given this unit circle here, pi over 4, the cosine is square root of 2 over 2, the sine is square root of 2 over 2. Now let me shrink that a little bit, and I'll just move it up to the side up here. So these two values, like we said, we're looking at pi over 4. This is the cosine, and this is the sine. It's the order that it comes in. So what I would have here is x would equal 3 times, and I would substitute in here square root of 2 over 2, and y would equal 3 times square root of 2 over 2. Thus, when I simplify, nothing cancels out with one another. B would be my answer choice here. By way of the calculator, if you went down to calculator 28, plotting points, polar and rectangular, and opened up that graph or that calculator, specifically I'm dealing in the mode of radians, so I need to swap this over to radians, and also need to go to the wrench and make sure I'm in radians there. Okay, now that I'm in radians, the polar point was 3, pi over 4, pi divided by 4. Okay, I'm in caps. Let me change this so the pi symbol actually comes up. Pi, there we go. And so what does that tell me about the x and y values? That they'd be 2.12, which if you type that in the calculator would be 3 times the square root of 2 over 2. I would be willing to bet 3 times the square root of 2, all divided by 2. That is in fact 2.12, and all that changed. So we got number 1 correct. Let's try number 2. It says find the rectangular coordinates for the point 10, 52 degrees. Alright, well this time I need to have circles out to 10, which I only have 1, 2, 3, 4 lines. So I'm going to count by 3s. So this is 3, 6, 9, that would be, whoops, not 10, that would be 12. So 10 is going to be a little bit larger than 9 at 52 degrees. If I label the degrees here, I would have 15 degrees, 30 degrees, 45 degrees. This would be 75 degrees. 52 degrees. It's going to be in between 45 and 60 here. And the 10th circle would be just a little bit past 90. So it'll be somewhere kind of floating around right in here, this general area. That would be our point B. This says find the values in rectangular. So it's just the same formula we used last time. And you know what I should have done last time, I did not do it, is to show you what we're trying to do is find the values in terms of an x-axis and y-axis. In terms of x and y, where that point would be located. That's ultimately what we're trying to do here. Let me go back very quickly to the previous problem, and I'm going to show you this. Over here, the values that we came up with at 2.12 and 2.12 for x and y, what that was referring to is my x and y axis here and here. that this would come down and it would be just past the value 2. If I measured that down, measure this across, you can see it's just past that circle there on both sides. So that's why that value, were these two values, 2.12 and 2.12. They're just past those second circles. That's what we're finding out there. Let me get this a little bit drawn accurately. Okay, so now I'm trying to do the same thing here. So if I were going to estimate, again, my picture is not accurate or exact here. I had to estimate just plotting it. It looks like it's going to be around 6, and over here 3, 6, maybe around 8, I'd guess. So we could take a guess that's going to be C, but if we want to know for sure, we'd follow our formulas that x equals r cosine theta, which means the x would equal 10 times cosine of 52 degrees. And I'll go to the calculator for this in a second. The y value would be r sine, which means our y value would be 10 times the sine of 52 degrees. Come over to our calculator. I'm going to refresh this. When I refreshed it, put me back in degree mode, which is what I need to be in. They gave me a polar point. So 10th circle at 52 degrees. It looks like the point is 6.16 and 7.88. Our guess was correct. So that would be our guess here. Say x is approximately 6.16 and y was approximately 7.88. All right, and number 3 in the bell ringer. It says find two pairs of polar coordinates for C, and this is a rectangular coordinate. That's an x and a y. Whereas the previous problems where we were dealing with polar, r and theta, on this particular problem we'll be dealing with x and y. And it says find those values between 0 and 2 pi. So if I wanted to graph this one, I would need an x and y axis. This says go 2 units left and 5 units up. 1, 2, 1, 2, 3, 4, and 5. It's my x-axis, y-axis. Here's my point C. We want to know if we were going to find this in terms of polar coordinates, what would that value be? So we need to find the radius here, if you will, or hypotenuse if you think of it like a triangle. If you think of this in terms like a triangle here, we need to find out what's the radius and then also what's the theta. So we're looking for r and theta here. That's what we're looking for. So how do we do that? Well, we know that the x value is -2. We know the y value is 5. So if we do Pythagorean theorem, our r value will be the square root of x squared plus y squared. That's always our formula. So in this problem, it's the square root of -2 squared plus 5 squared. -2 times -2 is 4. 5 times 5 is 25. So we're looking at the square root of 29, which I do not think can be reduced. It's going to be some value between 5 and 6. Some value between 5 and 6, which immediately throws out these options. The radius had to be longer than 5. So these are out. So we're dealing with 5.39 as our radius here. And now for the theta, since it's on the left side, since theta is less than 0, I'm sorry, since x is less than 0, since x is negative, for our theta, we're going to do the inverse tangent. And I'm looking at the answer choices, it appears they're in radians. So I'll do the inverse tangent of y over x, and then I'm going to have to add pi. So what's going to happen in the calculator is it's going to calculate y is 5, x is 2, -2, excuse me, and then we'll add 3.14 to the answer to see what we come up with. So I'll just use this calculator. It'll do all the calculations for me. I go rectangular this time. The value was -2, and the y value was 5. I need to be in radians. That's what it looks like the answers are to me, radians. And I'm going to move this over to radians. Okay, and so what does that tell me? My radius is 5.38, which is the square root. I'm hopeful is the square root of 29, square root of 29, 5.385, yep, that's it. And then the theta, it's going to do exactly what I told you, and it gets 1.95. 1.95 is what it solves here for theta. So 1.95, here it is, D. Now if you're wondering, where does this answer come from? Well, if you have a negative magnitude, that means it's looking at it. A negative magnitude is kind of like thinking where you first were looking this direction, but then you go across. Now how do you get a negative magnitude? Well, you add 3.14 to this answer. So if I take my theta here, my theta 1, and add 3.14 plus pi, I get 5.09, which is that answer, which is just saying, okay, what if we wanted the negative magnitude? That means that we'd have to add another angle all the way around. So instead of stopping right here at point C, I would go around this way one more time. So I would need to take my theta and add pi to get there. And that would take me all the way around. Thus we would get that second answer. Chapter 12. Specifically today we're going to look at lesson 12.1, estimating limits graphically. So we've seen some limits specifically on lesson 1.3. Well, we're going to bring them back as an intro to some calculus here. We're going to look at today one-sided limits and two-sided limits. So the first thing that comes up on number 1 is it says estimate the limit as x approaches -7 of 4x plus 1 using a graph. And I have one here for you, but support your conjecture using a table of values. And I want to make sure you know how to do this if you were at home on your own calculator. So what you would do when you're estimating a limit is the inside right here, that refers to f of x. So normally this would be written, if you remember, in the format of the limit of f of x as x approaches some value. That's normally how we would write it, and then we would say whatever it equals. So notice here what's happened is I have substituted for f of x with this 4x plus 1 right there. So that is f of x as I shown right there. That is f of x. So what I'll do here on my Desmos is I'm just going to type in f of x equals 4x plus 1. And I'm going to scoot this over just a hair so we can see what's happening. And so there's our graph. And we want to know specifically what's happening at -7. And so I could look on this graph. I could just kind of zoom it in here. Let me make sure. I want to be able to see -7 specifically. So I'm just going to go from -10 over, and then on the y values, let's see here. It looks like we need to get lower. I'm going to change this to a -30. Okay, so here's -7, and we want, let me slide out, let's see if it'll ever show a -7. Well, it doesn't seem to do so. At -7, you could come over here, or we can just touch the graph. At -7, it appears to be -27, and that would be our answer for this limit. I'll walk you through why. But if you needed to get a table, what you can do here is, I believe if you hit edit and hit that table, what's going to happen is the values will pull up. Now when we do a limit, you want to be approaching that value from both sides of the graph. What do I mean? Well, from the left of the graph we have a value -8. I'm going to put -7 right there. And from the right side, -6 would be the next number. And so you just want to pick numbers that get closer and closer to the value of -7. So you can kind of see how as I go, these values are getting closer and closer, and that's what you would continue to do. So we'll have like -7.1, -7.01, and you can kind of get an idea of what I'm doing here maybe. -6.99 and -6.9. So as the graph closes in closer and closer, we get finally to the value of, well, where is it? I don't know where -7 went. Maybe if I zoomed in here, you could see these values. Oh, there it is. And now I'll zoom back out. Well, that didn't work. One more time. Well, that doesn't seem to be working, but you can see as we get closer and closer, it's approaching negative 27. And so that would be our solution here to to this limit. It would be negative 27. Not only does the function exist at that point, but the limit means that's where the graph approaches. As you close in on that point, here's negative 7 right here. As the graph approaches it both from the right side and the left side, this graph is approaching that point, which happens to be negative 27. And so that would be our answer. So the limit, as I could say f of x there, but I'll write 4x plus 1. As x approaches negative 7, the answer is negative 27. Now, it won't always be the function on the graph, as we'll see later. But this first one's really simple. Now, I'll let you try one. We'll call this DOL number 1. Now let's look at example 2. So let's take a look at a limit where the graph does not actually equal the function value. So here we have a new equation. So here's f of x. And it's x squared minus 16, all that quantity divided by x minus 4. So this time when I go over here to my calculator, I'm going to type in x squared. I'm going to go ahead and hit the division sign now just to make sure the whole grouping gets divided here, the whole quantity, x squared minus 4. Now, when I type this in, my values aren't looking right now because I want to know when it's approaching 4. So I'll start with the value 3 here, and then I'll have like 3.5, then we'll call it 3.9. I'm just picking values that get closer and closer to 4. And then this will be the value 4, and then 4.01, 4.1, 4.5, and 5. So you can just kind of see I'm getting closer and closer here on my values, and I'm going to take this graph and zoom in. As we get closer and closer to this value 4, the graph appears in there to be approaching the value 8. That's what it looks like to me, and the table is showing the same thing. But we can, if we zoom in here, what's going to happen when I get to 4, you'll see that it has an open circle, which means the graph is undefined there. This is a removable discontinuity, if you remember that from lesson 1.3. So this has a removable discontinuity there, and at 4, it's undefined. The function itself is undefined, but that does not mean the limit is. Because what happens is we zoom in on that spot as the graph approaches this point. We can estimate the limit, which again, the limit does not mean where does the graph actually exist, it's where is the graph approaching. This graph is approaching the value 8. So even though this is undefined, we would say that the limit of x squared minus 16 over x minus 4 as x approaches 4 will still equal the value 8, even though the graph itself was undefined. So just because the graph is undefined doesn't mean that the limit will be. So it can exist even if the graph itself does not. So I'll let you try this one. We'll call it DOL number 2. Estimate the limit. And here you should have a picture that matches with it. Alright, now as we enter into example 3, let's learn about just kind of some rules here. It says here, independence of a limit from a function value at a point. And what this is trying to show you is that given all 3 situations here, where you have a graph, kind of like the last problem we saw, example 2, where you have something that's undefined at that spot, as long as the graph from both sides, both the left side of the graph and the right side, is approaching this point, L will be the answer to the limit at the value c. As the limit of this function as it approaches the x value of c, the limit would be the value L. And now on this second situation, it's showing you the same thing, but we have the graph itself actually defined way up here at the value n. Well, the limit would still be the value L. Even though the function itself exists at n, the limit would be L because that's where the graph was approaching, both from the left side and from the right side. The graph was approaching this point here. Even though the function itself does not exist there, it exists up here. The limit here would be L, even though the function value would be n. And here, this function would be undefined. So if you're wondering why is that G, why is that F, they just called this equation F here. and this one g. All right, now let's look at equation h. So now you have a function and it's defined at all points. Well, as you approach this value c, you can still see it's approaching this value L, so again, the limit would be L. So it doesn't really matter what the one point is when you look at limits. What you're doing is evaluating where the function is approaching and where is it going from both the left side and the right side. So with that, we have different names. We call the left-hand limit, and it'll be represented by this as x approaches c with a little negative. That would be the left side, and if it were a plus, that would be the right side. Again, all this is reviewed from lesson 1-3. If we have a left-sided limit that equals the right-sided limit, we have a limit at that spot for the function. This is only true if the left hand equals the right. If the left does not equal the right, then we do not have a limit of that function at that point, which we'll see as we go along. So here's part A. Given this graph, which is this equation f of x, we want to estimate the left-hand limit, the right-hand limit, and if we can, determine the entire limit. So on this graph, as we're looking at the value 1, as this graph approaches the value 1, what we can notice is the y values here. From the left side, it's approaching this y value right here, which they haven't labeled this, we'll label it a -2. Which means the limit of f of x as x approaches -2 from the left side, the y value it's approaching would be -2. That would be the left-hand limit. That's the left-hand limit. Now on the right side, I'll do this in red, on the right side the graph is approaching 1 this way to this point here, which this would be 1, 2, and we'll call that 3. Okay, so as from the from the right side, as x approaches -2 from the right side, that's what that plus right there means, the limit would be 3. This would be known as the right-hand limit. Right-hand limit. Now, because the limit of f of x as x approaches -2 from the left does not equal the limit, the limit of f of x as x approaches the -2 from the right side of the graph, since they were not equal to each other. Because of that, let me write since. It doesn't look like since, it looks like sine. Here we go, let's try this one more time. Since the limit of the left side does not equal the right side, the overall limit does not exist. Limit of f of x as x approaches, I just realized I was writing -2, I need to change that to +1s, does not exist. And so now let me go back here. I wrote all these -2s. I should have been writing -1s. I apologize for this. Let me replace all of those. Okay. Now I got that. We're talking about as x approaches 1 from the left side, 1 from the right side. 1 from the right side and 1 from the left side. That's how I should have wrote it. Because these do not approach the same point, the overall limit at 1 does not exist, but the left hand does. The left hand's value, the left hand limit is -2. The right hand limit is 3, but the limit as x approaches 1 from both sides would not exist. All right, here's part B. So looking at this graph, as we close in on 0, that's what we're looking at. The left hand limit would exist. We're approaching a point. Specifically, we're approaching the point -1. So from the left side, they call this function g of x. As x approaches 0, the y value that we're approaching is -1. This would be our left-hand limit. I'm going to abbreviate here, left-hand limit. Okay, now from the right side, it's approaching the same spot. So limit of g of x would also equal -1 as x approaches 0 from the right side. Ooh, I forgot to write the left side over there. Okay, this would be called the right-hand limit. Right-hand limit. Now, since the limit of g of x as x approached 0 from the left side equaled the limit as g of x limit of g of x as x approached 0 from the right side. Since that is true, what does that mean? That means the limit of, not f of x, g of x as x approaches 0 would equal -1. That's because these two are equal. And I just realized I haven't shown you how, this is called piecewise, and it's been a long time since I've shown you how to graph that. If you go to your pre-programmed graphs, you could open up piecewise there, and that's how you could graph this function. So you would just type in the branches as we go. This is 2 branches, so in step 1, I'd put the first branch here, x squared minus 1, as long as x is less than 0. Let me put this as x is less than 0. And for branch 2, we would have 1/4 x minus 1 if x was greater than or equal to 0. Greater than, equal to 0. And so that's how you can get the same picture on Desmos. Now, here is one for you to try. Let's take a look now at a couple more rules and then another example. It says y limits at a point might not exist. A limit would not exist at a point C if it approaches the left and the right do not equal one another, which we just saw in the last problem. We saw that 3a, I believe it was. And we wouldn't have a limit if the graph would increase or decrease without bound. That means it approaches infinity, either from the left or the right. Finally, if it oscillates between 2 fixed values, we might not have a limit as well. So let's take an example here. This first graph, as you can see on the left side of it here, if you wanted to just graph this, the f of x here would be 1 over x minus 2 quantity squared. I'm going to leave and just get to a blank Desmos. So I just deleted those extra letters. Okay, so this graph would be f of x equals 1 over the quantity x minus 2 squared. That quantity squared. Okay, so there's our graph. Since it's approaching infinity from the left and the right, we would say the limit itself does not exist. So the left-hand limit, I'm going to call this one, they called it y here, the limit of y as x approaches 2 from the left side would equal positive infinity. The limit of y as x approached 2 from the right side would equal positive infinity. But because they're increasing without bound, we would still say the limit of y at 2 itself does not exist. Why? You might ask. The reason it doesn't is because the graph itself increases without bound on both sides of the x value, the domain value. Because it increases without bound. If it just increased without bound on one side, it still would not exist. It's just the fact that it increased on both sides without bound, meaning it's going to infinity on both sides, just doubles over that it does not exist. Okay, so this limit would not exist. And I kind of realize that it's kind of low there. Let me put that together like that. That would be the case on part A here. Let me label this. This would be the left-hand limit. We'll call this the right-hand limit. But the overall limit does not exist since left-hand limit and right-hand limit increase without bound. increase without bound. That's kind of the why behind it. All right, and so let's take a look at this graph now as we approach 0 here. I can see the left side here, the limit of, I'll just put 2 over x cubed, that'd probably be easier. As x approaches 0 from the left side, as we go from the left side, this graph goes down to negative infinity. As we look on the right side of 0, as we get closer and closer to 0, I can see this limit is approaching positive infinity. 2 over x cubed. As x approaches 0 from the right side, the graph or the limit would approach positive infinity. However, the limit of 2 over x cubed as x approaches 0 would not exist. Again, well, this doesn't exist for 2 separate reasons. First, the left hand and right hand do not equal one another. Secondly, they're increasing and decreasing without bound. Left hand limit, and this would be the right hand limit. So here's DOL number 4. Let's look at this, what's called oscillating behavior. Now this is one I've heard a different mathematicians describe this differently. I'm going to take this approach. I'll show you. When we go to find the limit of this oscillating graph here, that oscillating just means it's kind of going back and forth like that. If it approaches and gets smaller to one value as you go, so let me give you a bigger picture here. Let's just make this x times sine of x. Okay, as I zoom out here, you see how it's getting smaller and smaller as it comes in? I've heard it said that if the graph is oscillating but approaching, getting smaller and smaller towards one point, we will go ahead and classify the limit. So this graph, though it would be hard to say from the left, where is it approaching? Well, ultimately, because it's oscillating closer and closer to 0, we would say the limit of x sine x as x approaches 0 from the left is approaching the value 0, and I would say the same from the right. Now it is a little bit trickier. I've heard it described both ways. They're saying, well, how can we actually say that because it's going up and down? How can we say, well, because it is, let me put this on here as it goes from the right side, equals 0. I've heard it said because these values are getting closer and closer, meaning it's shrinking as you go. This oscillating is shrinking. I've heard it said that you can classify the limit. Now, others might argue and say you can't. And I'll let you decide. I like to say that we can because it is, as we get closer and closer, infinitely closer to 0, we can tell that this graph is approaching 0. So I'm going to go ahead and classify it that way. Say it can equal 0 here. Now that might not exactly follow some of the rules we saw earlier. I know this one says if it's oscillating between 2 fixed values, but the values aren't fixed to me. These values are ever shrinking as we go. So I would say the limit does exist on this one. Whoops, where am I? Now for you, I'll let you take a look. Am I on the right one? Here we go. I'll let you take a look on this graph, and for a second I'm going to actually show it to you so you can have an idea of what you're looking at. Cosine of 1 divided by x. I'm going to make sure I get this right. So 1 divided by x like this. X. Okay. I'll let you look at, here's the graph oscillating. I'll let you make up your mind on whether or not you think that limit would exist, whether it's approaching the same point or if the point would be different. But I'll let you make up your own mind for yourself. As we get ready for this next example, let's talk about the limits at infinity. What this is saying is if the value approaches a unique number L as x increases, then that means is that we're going off the screen to the right. As x approaches infinity, then we would have the limit approaching L. And so this is just telling you how to read it. And again, we saw this in lesson 1.3 and negative infinity you'll see quite often too. This is going to also be called the end behavior. So it says estimate the limit as x approaches infinity of 1 over x plus 1 plus 1. Okay, so this is not looking for both sides. It's only looking for as you approach the right here, as we go further and further to the right. So x is approaching infinity as you go right. So what's happening as this graph goes off the screen to the right? The answer is it's getting really, really flat. Remember that kind of question we were asking ourselves, it's either going to go up forever, down forever, or come to a point or flat along a point or a number. In this case, it's flat, and the y value it's getting flat on is 1. So the limit of 1 over x plus 1 as x approaches infinity would equal 1 here, because that's the point I'm getting really flat on, the y value that I'm getting flat on. Make that look more like an arrow. That still wasn't it. Let me try one more time here. An arrow as we approach infinity. All right, and so now let's try this next one. So we change up the equation. We're now 1 over x cubed minus 1, and as I look at this limit, again, I'm going to the right. What's happening as I go right? Well, this graph is getting really flat along this horizontal asymptote that happens to be crossing the y-axis at -1. So the limit of, as x approaches infinity, of 1 over x cubed minus 1 would equal -1. Notice I don't have to test it from both the left and the right. When you're talking about as x goes to infinity, you're just saying what's happening as the graph goes basically off the screen to the right. So here's another one, and this time I want you to look at this oscillating graph. This oscillating graph is not converging on a point like example 4. This one is not converging nor diverging. It's just staying between these two fixed values. So we're not going to be able to say where the limit's approaching, because you could say, well, it's approaching 1. Maybe it's approaching -1. This here should be a -1. Maybe it's approaching a 0 or something in between. No, the answer is this limit of cosine as x approaches infinity does not exist. And I'm going to say it does not exist since the oscillating, if I want to make sure I spell this right here, oscillating values are fixed, and they're fixed between, just so you know what I'm talking about, -1 and 1. Okay, so since the graph is going back and forth between 1 and -1, I would say this limit does not exist. So let me make sure you get that as the answer here. It does not exist because of how it's oscillating. Let me come back over here. This graph, if I zoomed out, you'd see it's oscillating back and forth between those values forever and ever. Now, had I had it like 1 divided by x on here, and we were looking at the right side, then I would say this has a limit, because these values are getting ever smaller and closer to the y-axis as we go. So that's just kind of a differentiation for you there. I'll let you try this one, a DOL number 6. 7. Bacteria. The growth of a certain bacteria can be modeled by the logistic growth function shown there, where t represents time in hours. Estimate the limit of b as t approaches infinity, if it exists, and interpret your results. So let's first go graph this and see what this graph is going to look like. So we have b of, we can call it t, we can call it x, but I'll just go ahead and copy it exactly as they have it listed. B of t equals 675 over 1 plus 135e to the power of -0.6t. So there's our function. As long as you start with b of t, you need to use the variable t as your independent variable there. And we have our graph. I'm going to zoom out a little bit so you can just see what this graph looks like. Oh, wow, there's a trick to it. This is the logistic function. It has, I don't know how to describe it. It's kind of like a mountain ridge, and that's very common for the logistic function. So there it is. There's our picture, and I will screen capture this for us so that I can copy it over here, and let me shrink this because this is just huge. All right. So now that I got this back normal, what we could say is this limit, as we go off the graph to the right, if we look, you can see it's getting really, really flat. And what number is it getting really, really flat on? The answer is, if you look at the y values, they're not changing there. It's 675. And I guess I could have shown you, it might have been helpful to show you a table here. If I start typing in some large x values, let's just go 100, let's go 1,000, let's go 1,000,000. You can see that it's approaching 675. So that'd probably be even a better table to show you here. We can now state with confidence that the limit of b of t as x approach, or rather t, not x, as t approaches infinity would equal 675. And what does this mean? This means if you're trying to interpret, what this means is the number of bacteria approach 675 as time increases without bound. You could say as it approaches infinity, but I'll just say without bound. As time goes on and on, the number of bacteria approach 675. So now here on part B, it says the population of a certain city is given by this function here. So P of t is going to equal 0.7 times 1.1 raised to the power of t. I'm going to turn this one off. Where time is in years. Estimate the limit if it exists and interpret your results. Now remember the last one we needed to zoom out to get that table. So I'm going to kind of do the same thing here. I'll do 30, 40, 50, 100, 1,000, 1,000,000. You can see it's not the same value this time. So as I zoom out, you'll notice this graph happens to be different. And let me go ahead and throw that one on there so you can see the difference between these two graphs. It's all right. There you go, a little bit lower so I can get the rest of that table one more time. There we go. So now let me shrink this. Okay, so this limit does not exist. The limit of p of t as t approaches infinity does not exist. Since, actually, I'm sorry. The limit we would say exists is just it goes up to positive infinity. Since we're doing just one-sided, we could say as we go to the right forever, this graph also goes up forever. So this one approaches infinity. This means the population increases without bound. As the time increases without bound. Come back so you can see that a little bit larger. There you go. And now here's one for you to try.